Hey, also in this problem we've got a frictionless piston cylinder device. It's a diameter of 0.1 meters, and there's a brick with a mass of 100 kilograms resting on top of it. And within the cylinder there's liquid water and water vapor in thermal equilibrium, and you know the height, the piston is 15 centimeters above the bottom of the cylinder. And what you're being asked to find is, we'll call it P1, the pressure within the cylinder, and the temperature, T1, within the cylinder. The area of the cylinder, it's a circular cylinder, so you've got A1 is equal to pi over 4 d1 squared. And if we do, let's do a force balance on the brick. We've got weight acting downwards, so the mass of the brick times gravity, plus the force of atmosphere, so you've got atmospheric pressure pushing down, times its area, so PATM times A1. And the sum of those two pressures will balance, because it's not moving, will balance the pressure acting in the upward direction, or in this case P1 times A1. So we look at it, you know the mass of the brick, you know gravity of course, and you're given the pressures and the areas. So we can solve for that. We can solve in this case for P1. I want to show you how to do this. It's a simple problem, but I want to show you how to use engineering equation solver. It's a software program to solve for it. And here's the program, and I've included all of my variables. I've got d1 is equal to 0.1, and I'm doing units in square brackets in meters. Here's my equation for area, the height, the atmospheric pressure, the mass of the brick, 100 kilograms, and g, of course, in meters per second squared. And I'm using units in the brackets because they save me so much time fixing mistakes when I screw up units myself. So once I've entered them in ease, I can hit the Control F button to get formatted equations. I can look at it as well. I've got d1, and here's my equation for a1, and so on. Let's enter this equation into ease. So I'll type it in. Note that one thing I don't have to do is solve explicitly for P1. So I'll type it m times the mass of the brick times g plus P atmospheric pressure times A1, and that ought to equal P1 times A1. And to make sure I did it right here, I'll hit Control F. Here are my formatted equations. So I've got the mass of the brick, the weight of the brick, plus the weight of atmosphere pushing down. The force of atmosphere is balanced by the force of pressure within there. So let's look at the units on all of these. So I can click this button right here called Variable Info, and I'll click that, and it shows me all my variable names, and the units are what I'm interested in here. And it knows the units for everything. It knows the height. Height, for example, is in meters, and pressure in kilopascal, and g meters per second squared. I'm going to tell it the area I expect ought to be in units of meters squared. So I'll say meters squared for the units. And I've got units for everything else, and I'll click OK. So let's do this. It is smart enough to know we want to solve for P1, and what it'll do, I don't need to explicitly solve for it algebraically. And it's smart enough to solve for it on its own. It's an iterative process. I don't need to solve for it explicitly. And I'll hit the Calculate button, and I'll click it. And here is my results. And one thing I'm noticing right now is it says one potential unit problem was detected. So I'm using the unit function, and this is saving me a lot of grief right now because it's saying you've got a unit problem, and I'll click Check Units, and what it's telling me if I open it up is that these units differ by a factor of 0.001. So for some reason it's sensing that I'm off by 3 orders of magnitude somewhere. And what it is the fact that I've got all my pressures are in kilopascal. If I go back to my variable information, I've got kilopascal here, whereas in my units of weight I've got m times g, which is newtons, and my units of area are meters squared. So I really want them into kilonewtons. So if I look at my equation, it's this term at the bottom. This term right here I expect it to be in newtons, whereas I'm specifying this term is kilonewtons, for example. So I can what I need to do is incorporate a conversion factor, 0.001 kilonewtons per newton, to fix that. And at this point, with that correction, no unit problems were detected, and I've got all my pressures in kilopascals. And what I'm calculating is P1 is 226 kilopascal. So if I come back, P1, if I solve for it, P1 is equal to 226 kilopascal. Now the second part, we want to figure out the temperature, and because we know there's liquid and water vapor and thermal equilibrium, for a given pressure there is a temperature associated with that, and I can either look them up in the saturated water tables, or I can do the same thing using EES, using a function I'll show you. So let's do this. We're going to say T1 is equal, and the function is called temperature, and the pressure is equal to P1, and we need to specify a quality. So we'll say x is equal, and let's say x is equal to x1, and let's say there's only, we can say, if I put it right here, let's say x1 is equal to 10%. So there's 10%. If I come back to here, let's specify it's in vapor liquid equilibrium, and we'll say x1 is equal to 0.1, for example. So that means only 10% of all of the mass of water within here, only 10% of that mass is in the vapor phase. So we'll come back, and 10% of the mass in the vapor phase, and I query it, and I'll come to the units, and the temperature in degrees C, which we would expect. Quality is dimensionless. I click OK, and if I click the calculate button, I come up with T1 is 124 degrees C. Let's say we'd also like to know, with a quality of 10%, we want to know what the total mass of water is in the system, in both the liquid and in the vapor phase. We want to figure out what M1 is equal to. Well, we've got an equation. We can say M1 times the specific volume is equal to the total volume, V1, and that's equal, the volume would be A1, the cross-sectional area of the cylinder, times H1. So the volume is A1, H1. So we know the area, we know the geometry of it, A and H, and the specific volume we can find, because you know both the quality and the pressure, and we can find it, we can query it using EES, or you could look it up in the tables. So let's say we've got V hat 1, and the function is volume. We'll say steam P equals P1, X equals X1. So here's V hat 1, and let's specify the units for it. We'll click there, and the units for V hat 1, we would expect cubic meters per kilogram. That looks great. So we get the right units. And if I hit the calculate button right now, I come up with a specific volume of about 0.08 cubic meters per kilogram. So we know V1 we can solve. We don't have to solve explicitly for M1, so I'll type that equation in. So here's the left part of it. M1 times V hat 1 is equal to A1 times H1. And let's check the units on everything. So I look at it, all my units are filled in. I think everything should be good. If I don't get a unit mistake, I can be fairly confident in my answer. And I'm coming up with a mass M1 is 0.01475 kilograms. So about something a little bit less than 15 grams for the mass in that fluid. So here's M1 equal to 0.01475 kilograms.